Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on December 26, 2025, about 4 days ago. It introduces Yume-1.5, a diffusion-based system that can generate continuous, explorable video worlds from a single image or text prompt, while staying fast enough for real-time keyboard-controlled navigation. The paper is titled Yume-1.5, a text-controlled interactive world generation model. Okay. And as we will see later, the way it compresses long history and speeds up sampling is what makes the whole interactive setup feel practical. Also, the author shared an official GitHub repo for Yume, and it is essentially the full project drop. You will find setup scripts and requirements, a web demo for single GPU use, and inference scripts for image to video and text to video with ODE or SDE sampling, plus fine-tuning and distillation code and notes on dataset preparation. On Hugging Face, you can grab the Yume 5 billion parameters 720p preview weights, plus notes on interactive world generation, with usage pointing you to the GitHub for full inference scripts. Figure 1 makes the promise concrete, because it shows Yume 1.5 behaving like a playable world rather than a one-off video. This figure lays out the full interactive demo panel, where a text prompt, a starting image, or an event edit all feed an autoregressive generator, meaning the next frames are produced step by step as you move. The left column lists the 3 modes. The right side shows example rollouts with keyboard controls overlaid for person and camera motion. Figure 2 explains why the data re-annotation matters, because the model learns different things from scene description versus event description. This figure shows a short video moment across 4 frames where a street sprinkler causes people to move aside. The lower text contrasts an original caption that lists static context, with a new caption from a vision language model, meaning an image understanding model that writes text, that focuses on the motion event. Figure 3 ties the whole system together, because it shows how Yume 1.5 stays controllable while keeping long video generation efficient. This figure lays out 4 panels that cover the model block, the training text setup, history compression, and inference. Panel A shows a diffusion transformer block that uses linear attention, meaning attention that scales more gently with sequence length. Panel B splits captions into event description and action description, so action text can be cached during streaming. Panel C and Panel D show chunked generation, with history tokens downsampled more as they get older, which keeps memory stable. Table 1 shows that the main win is controllability without sacrificing overall video quality. This table reports Yume bench metrics, where instruction following measures whether the camera and walking actions match the intended controls. The instruction following column shows Yume 1.5 leading the group. The time column also drops sharply for Yume 1.5, which fits the few step sampling goal for real-time exploration. Figure 7 shows that the joint temporal spatial channel modeling design keeps generation speed predictable as the video gets longer. The full plot compares inference time versus the number of video blocks, which means more historical context to process. The blue temporal spatial channel modeling curve stays fairly flat, while full context input shoots up and gets truncated near 1 number because it becomes too slow. The spatial compression line sits in between but still drifts upward. Alright, 2 takeaways stand out. Yume 1.5 shows that interactive world generation becomes practical when you compress long history with joint temporal spatial channel modeling and replace many diffusion steps with a few distilled steps so frame rates stay steady as the world grows. It also shows that text-controlled events can be cleanly separated from actions, improving control in real time. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.